see if I can.
Welcome, folks, to the Azure and AI Show. My name's Dan Ray. Almost 3.5 years ago, Frank Falvey founded the Azure and AI Show as a weekly discussion of either Azure or artificial intelligence topics. We chose something specific to Microsoft and something very, very general. And Frank became an MVP probably a year and a half ago after doing this show for quite a while and having numerous guests on. And today, I am happy to welcome several different folks that are presenting. And I invited Hal. Hal is a 30-year Microsoft MVP to join us from Arizona. Hal, welcome. Thanks for joining.
Why, thank you. It's a pleasure to be here.
We met, I want to say, through community, but then in person at the MVP Summit.
Oh, yeah.
If memory serves.
Yeah, that's generally how that all works. I mean, most people at the MVP Summit. In this particular case, this last summit, I had the distinct pleasure of sharing an Airbnb with Dan, and I'm going to forget everybody else's names, but then that's what I do. I forget.
I would have to recall the names too. I think John was the new MVP that stayed with, I want to say Simon, but that doesn't sound right. I'm totally spacing the host's name right now, but I'm sure I can look it up and we can give them a shout out too.
that's
so much fun. Yeah, so we've got three presentations.
That was a really pleasant time too. We stayed in this Airbnb, and we had James. What was his last name?
James Fox. So I remember James.
Fox. Yes.
Yeah.
Who came up with transportation from the various hotels and stay and other places people were staying to the campus and back, and that was a huge boon. My goodness,
Neil Spellings was our host. So Neil was our host, and Spellings is his last name. That's why I had the S on the brain. But James Fox, from Momentum, was our concierge. Van transportation, if you will, for the week. That was a lot of fun.
Oh, yeah.
Yeah. So it looks like we've got everybody here. Shri, I believe you are going first. And then we're going to have Yogi do a presentation. And then Ravi, you'll be third. Yep. Okay.
Sounds good.
And Shri, if you want to share your screen or presentation, I can make that appear magically on the screen here.
I just started sharing it.
Okay. Yep, there it is. And I'll click on add to stage. There we go.
All right. Welcome, everyone. My name is Sriharsha. I'm a senior business engineer at Meta. And today I'm here to discuss how we design closed loop LLM systems with GraphRag in mind. And just as a heads up, the presentation that I'm giving here is based on my independent research and my own interests, and it has nothing to do with my job role at Meta. So today we are going to explore one of the most exciting frontiers in AI engineering. So we'll move beyond simple RAG towards intelligent self-improving systems. So these systems combine the power of knowledge graphs with adaptive feedback loops. So this talk draws a comprehensive review of 30 recent research papers and industry case studies. So what we'll cover is fundamental foundational concepts, cutting-edge architectures, and real-world success stories. So let's dive into how we build truly self-improving intelligence. So here is our roadmap for today. So we will start by understanding why traditional LLMs and even standard RAG systems struggle with complex reasoning tasks. So then we'll explore how GraphRag addresses these limitations by leveraging knowledge graphs. So then again, we'll deep dive into what makes a system closed loop. So what is closed loop? So that means that the adaptive feedback mechanisms are embedded into this particular production systems that allow these systems to learn and improve continuously. I will also show you real architecture blueprints and case studies from production deployments. So we'll be honest about the limitations and challenges, and finally, we will take a look at where this field is heading. So let's get started. So let us start with the first problem here. So despite remarkable progress that is being made in the field of artificial intelligence, large language models face three persistent challenges that limit their reliability in production. First is hallucination. Models confidently generate information that sounds correct but is factually wrong sometimes. Second thing, knowledge currency. So models are frozen in time at their training cutoff and cannot access the current information. And coming to the third one, perhaps most critically, reasoning gaps here. So when you need to connect multiple pieces of information across different entities and relationships, standard LLMs usually struggle. And these are not minor inconveniences, right? So in domains like healthcare, finance, and legal, these failures can have serious consequences. So this brings us to the limitations of traditional RAG. So coming to traditional RAG, it is a significant step forward when compared to the regular LLMs, right? By grounding LLM responses in retrieved arguments, RAG reduced hallucination and improved factual accuracy. However, it has fundamental limitations too. The pipeline is linear and open loop. The system retrieves documents, generates an answer, and moves on. It never actually learns from whether that answer was good or bad. It just relies on semantic similarity over flat text chunks, which means it misses the rich structural relationships between entities. And critically, it performs single shot retrieval with no mechanism for error correction. For an example, like when a query requires connecting information across multiple documents or entities, what we call multi-hop reasoning, traditional RAG falls short of it. So this is where a new approach becomes essential. Enter graph RAG, which is a structured knowledge that meets generative AI. So this is where graph RAG enters the picture. So instead of treating your knowledge base as a flat collection of text chunks, GraphRag organizes information as a knowledge graph. So this is a structured network of entities connected by meaningful relationships between each other. So this enables something traditional RAG simply cannot do, which is like multi-hop traversal. So the system can follow paths across connected entities, discovering relationships that would be invisible to vector similarity search. When integrated with LLM generation, this produces contextually richer, more accurate responses. So the research that I have made shows consistent performance gains of 8 to 15% over traditional RAG approaches across various benchmarks. So this is especially true for complex multi-hop scenarios. So how do we actually build these systems is what we're going to discuss next. Now that we understand the power of GraphRag, let's explore how it's actually built. There isn't just one way to implement GraphRag. There are five distinct architectural patterns emerging from research and industry. Each offers a unique approach to integrating knowledge graphs with generative AI, tailored for each different use case here. For instance, combining a knowledge graph with semantic clustering is excellent for data analysis, while a hybrid approach with vector and keyword search is excellent for enterprise knowledge discovery. So it boils down to choosing the right pattern uh, that is crucial for maximizing the performance and efficiency in your specific application. But how do we make these systems truly intelligent and adaptive? That is what we discuss now, which is what we call closed loop. So the real leap forward comes when we move beyond static pipelines to closed loop systems. An open loop system simply executes a sequence of steps and stops, never learns from its outputs actually. In contrast, a closed loop system continuously uses its outputs to improve its future performance. This iterative improvement is driven by five core components: plan, generation, execution, feedback, acquisition, error diagnosis, and finally updating or replanning. So this design principle, borrowed from control theory, always allows AI systems to adapt and evolve. But what kind of feedback drives this continuous learning? Let's know more about it here in this slide. So the intelligence of closed loop systems hinges on the quality and the variety of its feedback signals. When we actually categorize this into a certain segments, like probably the four that we're talking about is the more significant ones here. So the first one is explicit user feedback, like direct corrections from a clinician in MedGraph RAG offers clear guidance, and implicit performance signals such as LLM's confidence scores allows for self-optimization without human intervention. Third one, task-based metrics. So, for example, like accuracy on a specific benchmark, measure real-world effectiveness. All this comes under the specific task-based metrics category. And retrieval quality signals is where we assess the relevance of retrieved information and ensure the system is always working with the best context. So understanding these signals is the first step. Next, we need to know how to use them effectively. So once we have these rich feedback signals that we discussed earlier, so the next challenge is to design mechanisms that allow these systems to learn and evolve. Several powerful adaptation mechanisms are proving highly effective here. So joint optimization, CNN systems like GRIL, uh, trains retrieval and generation components together, leading to state-of-the-art performance. Second one is the multi-armed bandits. This approaches balance exploring new strategies with exploiting known good ones, ensuring continuous improvement there. Self-healing RAG system is another one, or we just call it SHRAG. Can even self-correct by monitoring their own output quality and refining retrieval automatically. And the fourth one is casual dynamic feedback, as in CDF RAG. So what this does is intelligently routes feedback to the specific component that needs adjustment. So these mechanisms are the engine of continuous learning, but let's discuss on how they manifest in real-world architectures. These adaptation mechanisms come into life in very edge architectures. Like EchoRAG, for example, uses iterative refinement where generation outputs directly inform the subsequent retrieval cycles, which creates a true learning loop there. Think on Graph 3.0, which employs a multi-agent approach with specialized agent co-evolving through interaction to enhance overall system intelligence. Agentic KGR takes this further, using reinforcement learning agents to collaboratively build and refine knowledge graphs in real time. And coming to the last one, hybrid AI systems combine the deterministic reliability of rule engines with the generative flexibility of LLMs. All of these connected by intelligent feedback loops. So these architectures represent the forefront of building truly adaptive and intelligent AI systems. But what kind of performance gains are we seeing from these advanced designs? So we have explored the architectures, but not let us take a look at the concrete numbers. So these are not just theoretical gains, they are validated across multiple benchmarks. Grill achieves state-of-the-art performance on 3 major question answering benchmarks, especially for complex multi-hop questions. MedGraph RAG delivers a 10% improvement in fact accuracy checking and 8% in medical question answering across 11 datasets. So in healthcare, these margins saves lives. GNN RAG achieves a remarkable 9x reduction in token usage, allowing a 7 billion parameter model to match GPT-4 level performance. So this is extraordinary efficiency. And CEDAR's Seena's escargot agent achieved 94.2% accuracy on multi-hop medical reasoning compared to GPT's 49.9%. So these are not incremental improvements, and they represent a fundamental step change in what is possible. So now let us see how these translate into real-world impact. So moving from benchmarks to real-world impact, let us look at NASA. So they faced a classic enterprise knowledge problem. So where thousands of employees, overlapping projects, and deep institutional knowledge buried across various documents. Finding who knew what was nearly impossible. So NASA built a people RAG knowledge graph. So capturing structural relationships between people, projects, departments, and their area of expertise. So their graph RAG pipelines extract and enrich personal data from unstructured sources. So the key advantage over vector-only RAG, when someone searches for who worked on autonomous space robotics, the system traces verified project histories, expertise, and collaboration networks through multi-hop reasoning. So the results are dramatically faster, and it was giving a faster response in onboarding, smarter internal mobility decisions, and rapid identification of in-house experts. So this shows the power of structured knowledge in action. Next, we'll see how this plays out in healthcare. Healthcare is where GraphRag's impact becomes most tangible. Priscina Health built P3C, a provider patient copilot that connects medical records with social and behavioral data in real time. Using multi-hop reasoning, it traces patient outcomes through layers of cause and effect, not just clinical data. So, coming to the result, a 1% monthly reduction of HbA1c for type 2 diabetes patients, which is 12 times faster than standard care. At Cedar Sinai, researchers built a knowledge graph with over 1.6 million edges, integrating more than 20 biomedical sources for Alzheimer's research. So their Kraken system surfaced new treatment possibilities, including connections between genes, drugs, and clinical trials that would have been invisible to traditional approaches. So these are not incremental improvements. They are changing how we practice medicine. But it is not all smooth sailing. We need to be honest about their limitations too. Now, let us talk about the critical limitations. Because understanding these is just as important as understanding their capabilities too. So first, the scalability wall. Graph construction and maintenance costs grow significantly with data volume. So building a comprehensive knowledge graph requires deep domain understanding and expertise, which is both complex and resource intensive. Second is the latency tax. GraphRag introduces approximately 2.3 times higher latency compared to traditional RAG, and adding real-time adaptation increases this further. So for latency-sensitive applications, this can be a deal breaker. Third, graph quality fragility. So entity linking errors propagate through the entire system, and LLM-generated knowledge graphs can introduce noise entity and hallucinated connections. So, and fourth, the interpretability gap. As these systems become more complex, they become increasingly difficult to explain, debug, and audit. In high stakes and domains, this opacity limits trust and adoption, and there are even more hard truths to be faced. So there are additional challenges that practitioners need to be aware of. So the feedback quality paradox is real. If your feedback signals are noisy, biased, or inconsistent, the system will learn the wrong lessons and actually degrade over time. So this is particularly dangerous because it can happen gradually and be difficult to detect. So positive feedback loops are another serious concern. Errors can amplify through feedback cycles where a bad retrieval leads to a bad generation, which leads to a bad feedback, which makes retrieval even worse. So, catastrophic forgetting is the risk that continuous adaptation causes the system to lose previously learned knowledge. So, you fix one problem, but you actually create three new ones. And there is the information overload paradox. So, retrieving more context from the knowledge graph does not actually help always. Beyond a certain point, additional information introduces noise and can actually confuse the LLM. So, how do we navigate these challenges? So, the best practices is how do you actually build these graph systems that perform reliably in production. So coming to the best practices, the key is to avoid common pitfalls and focus on foundational strengths. Never let an LLM invent on your ontology. That's a recipe of chaos there. So instead, design your schema with domain experts upfront for structural integrity. Also implement multi-stage verification for all extracted entities and relationships. This ensures data quality before it even enters the graph. Finally, use hybrid retrieval, combining vector search, keyword search, and graph traversal for maximum robustness. This approach ensures you're leveraging the best of all worlds. So these practices will generally help you build a solid foundation, but the feedback loop itself needs its own set of best practices. Now let's talk about engineering the feedback loop itself, because it is where true intelligence emerges. First, design for stability from the outset. This means implementing adaptation rate limits, regularization, and anomaly monitoring to prevent the system from spiraling out of control. Second, distinguish your feedback sources. Not all feedback is equal, and using casual reasoning like in a CDF RAG helps route feedback to the right component for targeted adjustments. Third, balance real-time and offline adaptation. Your your need immediate so you need actually an immediate adjustment for personalization, but also periodic batch refinement for systematic improvements. And finally, actively prevent catastrophic forgetting. Techniques like experience replay and elastic weight consolidation ensure the system learns new things without losing the old knowledge. But remember one thing, like, all this engineering comes with a cost, and that brings us to the efficiency equation. So the efficiency equation is crucial because in the real world, cost matters as much as performance. Traditional RAG is your baseline: low latency, no graph construction costs, but limited performance on complex tasks. Basic graph RAG offers performance gains, but introduces higher latency and significant graph construction investment. So GNN RAG is a game changer here, achieving a 9x reduction in token usage while matching GPT-4 level performance with a smaller model. This means extraordinary efficiency. So closed loop graph RAG system delivers the highest performance, especially on complex multi-hop tasks, but they also demand the highest investment in infrastructure and maintenance. This right choice really depends on your specific needs for accuracy, latency, and budget. So what's next in this particular field? How is this field evolving is what we're going to discuss next. So let's look at where this field is heading, because the pace of innovation is incredible in this area. So multimodal feedback is a major frontier. Future systems will integrate feedback from text, images, structured data, and even effective signals, leading to much richer adaptation. Neurosymbolic reasoning is another promising direction. So, combining logical reasoning with neural learning could address the interpretability gap that currently limits adaptation in high stake domains like finance and healthcare. So, federated learning will enable privacy preserving feedback aggregation across organizations, allowing collective improvement without sharing sensitive data. And temporal knowledge graphs will model how knowledge evolves over time, which is essential for dynamic domains where facts change frequently. These advancements will make our systems even more powerful and adaptable. So let us continue our look at the future, focusing on how these systems will become even more tailored and reliable. Deep personalization will move beyond simple user preferences to rich models that track how a user's knowledge and needs evolve over extended interactions. This means the system truly understands you over time. So uncertainty quantification is essential for trustworthy AI. So future systems should provide calibrated confidence estimates for every output, enabling users to make informed decisions about when to trust the AI and when not to. And graceful degradation means designing systems that maintain partial functionality when individual components fail, rather than producing garbage output. So finally, the most impactful advances will come from combining insights from control theory, cognitive science, human-computer interaction, and deep domain expertise. This interdisciplinary approach is key to actually building truly robust and intelligent systems. So, what are the most important things to remember from today's discussion? First, GraphRag is not experimental anymore. It is production ready and delivering measurable results in healthcare, enterprise, and research. Second, closing the loop is transformative, but it requires careful engineering. You need to think about stability, feedback quality, and catastrophic forgetting from day one. Third, the fundamentals matter most. Start from a well-designed ontology built with domain experts. Use hybrid retrieval for robustness and implement multi-stage verification for graph quality. Fourth is invest in feedback loop stability as much as you invest in raw performance. An unstable system that occasionally performs brilliantly is worse than a stable system that consistently performs well. And coming to the fifth one, the future belongs to systems that can reason over structured knowledge and learn from every interaction. This convergence represents a fundamental shift towards more intelligent, reliable, and useful AI systems. Thank you for joining me on this journey today. And thank you for this attention, and I hope this talk has given you a clear picture on where closed-loop graph-like systems stand today. Happy to take any questions, and thank you, Azure and AI Show, for providing me this opportunity.
Excellent presentation. Thank you.
Awesome job.
Thank you.
Awesome job. Yeah, I like the fact that you talked about the different. I think I'm muted in one window, but I should be audible in the other.
Yes, you are.
Good. Cool. And Larry's joined us. He's in the same room I am, so we're we're hoping not to cause a echo here. But great job.
Thank you.
Definitely.
Thanks.
Yeah. Would Yogi, would you mind if I have Larry share something for like 2 or 3 minutes real quick?
Definitely, sure.
Excellent. Larry, if you go to your share, it's like the little, yep, and then screen. And then, okay. And then I think you got the whole screen. Yeah, display or something. Entire screen, yeah. Yep. And then just share, and then I'll put it up on the screen here. Larry's got the the Windows Sandbox installed here. Shri or Yogi, Hal, Ravi, have any of you played around with the Windows Sandbox or heard of it?
Oh, absolutely. It is a godsend. I use it pretty much weekly.
Cool.
It's just the coolest thing. It's you get for me it's I get something weird in email, and instead of clicking this link, I go fire up the sandbox, put the link in the sandbox, go ahead and click it. And if it corrupts the crap out of the sandbox and takes over all sorts of evil stuffs and so forth, I reach up and click the little button, the sandbox, and all the evil goes away. It
exactly.
vanishes.
It's isolated, right?
It is a superb piece of software, and I've even written an article about that. That its uses are limitless and well worth the effort of people to pay attention.
Yeah. And that Larry and I were talking about it. The nice thing that differentiates it from Hyper-V or VMware is that you don't have to install anything.
Exactly.
The sandbox just
That's
has the same version of Windows that you have. So Larry, if you close the sandbox, we'll get the message about like everything goes away. And then if you open the sandbox again, what Larry had up there was BG Info, which is a utility by Markus, and it just displays a bunch of characteristics about the computer it's running on. So Larry has a real computer. Larry, do you see the little black window at the very bottom? Can you bring that up? Very, very bottom of the screen, like on your taskbar.
Sorry.
Is it the black window? That one.
Oh.
That should have my computer name in it. If you click on it. It's like to the right of the browser. Yep. To the left of that.
Oh.
I think that's it.
That's
No. Just open a Windows key R. The Windows key R. Windows key and R, and then hit enter. That should be CMD. So that shows the real computer name, which is D-Ray Surface with a 3 at the end because it's a Surface Laptop 3. And then Larry, if you go into the sandbox, just tap into the sandbox window and do the same thing, Windows key R. and then type CMD space /K space host name. And then /K space host name. And then enter. Just try enter. It'll either error out or it'll open. There it goes. And that shows the host name, right?
Yeah.
Yep. So you can see that the host name of the sandbox is different than the real computer, and how, like you said, you can do things like I got an email or I was told to go to a website. You could put that into the browser here and then just close down the sandbox. So I thought if folks hadn't seen that, that might be a quick demo to share with everybody. Thanks, Larry.
That's nice, actually. It's pretty lightweight.
Pretty cool.
Yeah, it's pretty lightweight.
Yeah.
Yes, thanks.
Excellent. Okay. Shri, or sorry, Yogi, let me put up your slides here.
Yeah, cool. I think I can just give a little bit of intro. Like I'm Yogiraj, go by Yogi, and I'm a tech leader at Instacart. Basically working very recently on the AI LLM use cases, and I wanted to take this stage today to let everyone know like how we use real-time LLM use cases to a grocery persona, and how we have thought about deploying these applications at scale. There has been like a lot on prototyping of using ChatGPT or let's say Claude models to do some kind of intelligence for prototype level applications. But when you start thinking on real business value, things take a little bit turn, and it has more than just deploying an LLM in production. And that's the whole premise. Like the way the slides are being set up is giving a little bit of more introduction on like what exact the foundation is and how it has helped Instacart to achieve like a global scale within US and Canada to run AI recipes or even chatbot. So for like a bit background to the audience, like LLM is mostly a text-based data source which it understands human language. It understands what human is asking as a query, and it's able to parse through a huge index corpus of text data. And that's what large language models are. And few of their models, examples are ChatGPT, Google Gemini, Anthropic, Llama. These are the buzzwords we all the time hear for last couple of years. Example use case for these LLMs is like literally, you need to give human language saying like create a healthy pasta recipe, and the output is completely AI generated with, you can ask for generation of image and a certain set of instructions on how to create this recipe. So why this topic matters, right? Basically, there has been a gradual shift of developing LLM applications from experimentation to real business impact. So enterprise demands like, okay, what is the ROI, or what kind of value you can bring out of deploying this at scale. But when you start taking a deeper look into this, it also comes with the reliability, scalability, and governance needed for enterprise. There are numerous laws an enterprise has to think about, and they have to make sure like LLM responds in a way which is more guided. And the third part to this presentation is more of a foundations, what we have developed, and Instacart use cases where this is deployed live in production. What LLM deployment in production is like unique is, traditionally all the softwares have been written in deterministic way. What I mean is, there is an if-else conditions. Everything is predictable because like it's more of a static decision making behind the scenes, and like the pattern or the deployment of these applications at scale has been traditional. But with LLM coming into picture, the output of LLMs is probabilistic. What it means, it gives you a probability for a user query, and you have to think through like how this change in the way of how you're going to use this real time, deploy this to real users, and how to make it more strategic. So as a part of probabilistic output, like now we have to think about validation layer, output parsing, or retry logic. So these kind of elements have become more prominent in the industry, as well as like the heart of this whole application is the cost you pay for the model, which is like ChatGPT or Claude, right? So the bigger the model, definitely its quality is better, but it comes with a cost. So there has, like, the industry has seen a trade-off. Like if you're dealing with, let's say, healthcare data, you might go with like small LLM model and not go with ChatGPT at all, because it's more specialized. It understands health data way better than more generic, bigger model. So these are the trade-offs you could see. And as a part of that, like, there has been new requirements where we have to have evaluations like hallucination, as Shri rightly pointed out in his previous presentation. Hallucination is a big problem with these LLMs, right? So if you give same query 3 times and run through LLM, there is like a high probability an output might differ for one of the queries. So you have to be more confident in developing these applications, and as a result, you need like high quality data, continuous evaluation, and real-time monitoring if there is a degradation in the experience. At high level, when we say like we want to develop an enterprise application which involves LLM, this is the like a typical workflow where model layer is more of LLM itself, which is like literally the model you choose for your application. It can be Gemini, Claude, ChatGPT. But above that, that is the heart, like model layer, right? But the retrieval layer is more about providing or grounding the whole LLM to a specific domain space. To give a very simple example, like we have a chatbot on Instacart surface. Instacart is a grocery, big grocery delivery service. But if you go to that chatbot today, it answers everything related to Instacart. So we have grounded that chatbot. Like if someone queries, what is the weather today, it will say like it has a guardrail to not answer that question. Else, people will start using Instacart chatbot in a way it's like a normal chat GPT, and it will blow up our entire application. So you have to put like in a grounding vectors, like show it like exact domain knowledge. Like we have grounded our entire LLM to Instacart Help Center, which is on consumer and shopper help center. Orchestration is pretty traditional, where we have an orchestrator which knows how to pull data from model layer, from databases, or even like some function calls from other services like microservices. After that, after orchestration, we come with a layer called evaluation, right? So as these systems are being deployed, what it takes to deploy those, like we run some offline tests. Like we have partnered with other third-party vendors which are pretty open source, like Brain Trust and all. They help us in understanding like if we have this kind of prompt, and if we upgrade the model from ChatGPT 4.1 to the new release, let's say 5.3, something latest, what is the degradation or what is the confidence with the prompt logic we have in production, so that the overall experience is great. Safety is pretty very vital to this whole workflow. We don't want to give output through LLMs which are not according to the policies. For example, if someone reports like they are into some serious situation, we want to make sure LLM respects that and does an agent handoff, so that a human can come in the loop with any kind of sensitive things. Monitoring, pretty standard, but the monitoring here has now added dimensions where we track more about drift, quality, and latency, as well as cost and anomalies. So these are the different segments we have to take account when we start thinking about LLM in production. I think I'll go a little bit short on this, because data retrieval and all this is something we ground our entire LLM. RAG solutions, embeddings, and vector store are the more technical terms, like exactly how you scrape a data so that LLM is able to query it, like what the human query is and what data it needs to search on. So data retrieval is more into the more specialized this data is, the more quality of your output through LLM you can guarantee to your end users. Very simple, like what we have done, right, in like how we are using today at Instacart. Very simple. So recipes you can think of is like, if you ask in your daily life someone a recipe, the way a recipe is communicated is very analogical to you speak to someone, right? It's not structured, it's like a non-structured data. And that's where the challenge comes, and that's where we start using LLM, where it helps in converting the raw text into a structured JSON, so that Instacart data models would understand what the entire data is being inputted, and how it gets mapped to all the data models, so that those recipes become shoppable. So on the left side, you could see like a simple recipe written in like very simple steps, which is not structured. We give a prompt saying like, you are an AI agent, which you are able to parse like a given data into certain parameters, which is title, ingredient, steps. And then you can see on the right side, you can get a more structured output. So this is very high level. I will go a little bit more into details on how this entire pipeline is being built, but that is the crux. On the side, like what has come to our attention is like how we are going to evaluate all these models at scale, right? So think of this like, if you are developing a recipe ingestion pipeline, we use almost like 10 to 12 prompts in different places. And we might have different versions of ChatGPT or let's say Claude or any kind of Gemini model, right? And we want to do some kind of upgrade because there is a new cheaper model. We want to evaluate like, is there any better new model which is suitable for this kind of sub workflow? So we have this brain trust which helps in giving the confidence score. So we have all these prompts into this platform. We have integration tests written, and it gives us like, if you change this model from A to B, what would be the improvement in the experience or degradation? It's a score. On online side, if this system gets deployed, we continuously monitor very contextual, like are there change in number of clicks? Or on CareBot side, are there more human handoffs because LLM is not able to auto resolve contacts? Or what is the CSAT? CSAT is just like a survey based method. And tier 3 has been like human in the loop, which is pretty traditional, where humans come in and they make an expert judgment call on the transcript analysis. So we have all this data, and they take look of top X use cases. On monitoring and observability, what we have done is like drift detection, like track changes in model behavior through various internal metrics. Latency cost has been always like a prime focus because like LLMs come with the latency. It's not like simple like it's a microsecond. We do see like if ChatGPT or if OpenAI goes down, we have a backup of queue. We have to process so much of data. We have to reconcile those data. Error categories has been a little bit more categorized these days, like classic failures, are 4xx and 5xx, but the error category has been like, how much is the hallucinations, or are there like basically safety issues happening? So we start sending this event, which has been very tailored towards LLM side of the world. With the interest of time, I will bring the audience today towards really like how we are using this in production, right? So we had a goal like 2 years back on bringing recipes to Instacart marketplace. What it means is why it matters, right? Why AI recipe generation matters. If an enterprise like Instacart wants to sign a deal with any kind of recipe platform, they have to pay a lot upfront. It's a licensing thing. And that's why like with emergence of LLM coming in, we had an option like, should we explore the AI recipes and see how it goes? So the success has been great. So we have been, doing amazing with generating almost 10,000 plus recipes, which are shoppable. So what it means is, these recipes, they have all the instructions, but all the products are one-click shoppable. You can get it from the nearest retailers. So this is the exact page you could see in production today. Like it's www.instacart.com/recipes. And you could see like, a lot of things are going in this page. Like this page is combined between these two. So this first and second slide, both are as like one big HTML. Here, what you would see like, the recipe title, the basic, image, all this is generated by AI today. And what it means is, we have taken like, if it's a season thing, like it's a summer, right? What is the highest SEOs, search engine optimization keyword being searched for breakfast today? And this is like, let's say fresh berries, oat milk, these are the highest kind of hits. So what we have given our LLM is like, hey, please generate like small standardized recipe with oat milk porridge and fresh berries, right? So it generated like a recipe with like a general text with a lot of ingredients, and of course we have a high quality on reiterating those. We ask LLM to generate most realistic image around that, and the rest of the thing becomes like a pipeline on how to make that like matching those ingredients to retailer catalog. So on this page you would see like Sprouts Farmer Market, which is just below this image, is the most nearest retailer store from your home address to basically you can shop all the items. So you could see whatever we have generated in terms of instructions, preparation, all this becomes more of an AI generated content at this point. Full ingredient list is something you would see what people talk in daily language, like half a cup of milk or pinch of salt. What is challenging is how you translate these like full ingredient list into like a shoppable thing where you have to convert all these units into more of machine readable, machine data format, right? And that's the challenge where AI helps us today, where you could see like multi option oat milk or regular milk, right? So this is something you always give options in your daily life, and we have to ground the entire prompt saying like if there is a multivariant option in a sentence, prefer the first one, and if first one is not available, go to second. So these kind of prompt tuning we have to do, and we have learned over a period of last 2 years, because we have seen so many variations in how users usually give input. And just to give a background, like we generate recipes from AI, but we also parse the input from retailers who are interested to ingest retail recipes into their storefront, application, or even ads recipes, right? So you could see like on the left side, like there are vague quantities, like what is fresh berries. Now fresh berries is such a simple term, but when you develop a AI ingestion pipeline, you have to think through like what prompt you should build so that fresh berries translate to just berries. So we have to say like the prefix like fresh or ripe, these should be ignored while you're parsing the text. Range 1 to 2 tablespoon, just prefer the highest one because we want to be safe. A pinch, so there are things we have grounded our LLM saying like ignore few things which are not most relevant to this pipeline. So on the right side, you would see like, the whole pipeline, like the LM output helps in 100% extraction, but also like quantities are normalized, like from 1 to 2 tablespoon goes into like tablespoon, like basically it's like 2. The unit has been grounded to 2. And catalog matches, like entire whole this output is matched to the catalog. So at high level, what we say is like, we generate an AI recipe. We try to define like what should be the standardized output, and basically we try to sanitize the text and parse this text, ultimately matching it to our Instacart data model. Where we exactly use LLMs is like, first of all, like generating blanket recipes using SEO, sanitizing the text, like 1 table of salt and pepper gets translated into an array saying like, if you see this text in the prompt, we say like split this into an array where 1 table of salt and 1 table of pepper. Now you can say like, okay, just build one prompt, big prompt, which is like, let's say 20 lines and do everything. It's hard to maintain. And that's why we have a ingestion pipeline, which does very specific things at a particular checkpoint of the pipeline. And then you can see on the last third bullet point where 2 tablespoons of organic baby sweet potatoes is converted into units, quantity, and then what is the core ingredient for that. So you could see like, like all these things have been really basically an enrichment to our knowledge base, where the learnings out of this is like where image generation is really hard. So when we started this 2 years back, we had very pretty much like name models to generate images, and people would question whether those are AI generated, right? So we had to bring in lot of evaluations for our image generation of recipes, where we first went with human-based eval. So what it means is literally we generate, let's say, a few hundred recipes in 2 weeks, and we spend 2 weeks with humans literally going through Excel sheet, like this is the recipe, this is the context, and is this image really good or not? So they would just in a column say yes, no, reject, we regenerate. Later on, we got smarter. We started LLM-based judging. What it means is, we bring the recipe title, description, and image, send the same to another model and saying like, if you have this context, give us the confidence score, like how good that image is. So this is more on the image side. On prompt iterations, we have like lot of prompting, which we eventually got better on, deciphering all ambiguous statements. Like quantity 8 to 10 close goes to 10 close. Brand filtering, we can't promote any kind of brand, right? So it's Nescafe coffee, we have to say like, if there is a brand, eliminate those while you're parsing and just ground it to just coffee term. Like dropping the descriptors like chopped salad, slide, like like sliced onion, all these things we have to start parsing. So the last bullet, like sliced tomatoes goes and get converted into tomato. there has been some limitations, as we have seen. Like there are so much like variations in the keywords people type. Like tomato is like tomato, like TOE, right? So there are things where our parsing ingestion pipeline flags, like we need your human intervention to understand these keywords. Do I have a couple of more minutes, Dan, or this is another use case, but I'm happy to.
You're doing fine.
Fine, right. Second use case where I want to bring attention to every audience today on this platform is, how we have developed a care bot, which is a chat bot, which helped us to reduce the operational cost of, serving all kind of things which goes bad with an order. So what common questions this chatbot today serves is, where is my order? I received the wrong item. Please help. How do I get refund? Like all policy-based questions. Can I, refund this, return this item? So I think these are the important questions our chatbot today responds. And the design principle for that is, we have this pipeline which understands like what is the user intent, because intent is important. If we are able to understand if my order never came, it means like missing order kind of persona, right? And we have to check whether we have to render a health center article which tells a policy, or invoke an API which helps in refunding the order. So understanding the intent would just determine the exact flow, whether it's like API invocation versus rendering a health center article, or even do an agent handoff. So the principle for this is intervention first architecture. So basically, we understand like are we able to intervene like intelligently and call an API to self-resolve this question. And the second thing is hard block agent policies, where things doesn't become sense. Like if there is a customer fraud, or if like the refunds are outside policies, we don't allow, like we give the right kind of connection or a response through AI agent, and then we block agent handoff. So in the context, like agent handoff is expensive. Like when you look at the operational cost at the scale, like today Instacart serves 26 million users within US itself. So you can imagine like what would be the operational cost to maintain like a site which helps in all kind of operation, like basically user queries. So I think today the carebot, I think this might not be really visible, but I would say like on the left side, like if what we do is like if a query comes, we see like if that query is resolvable through health center article, and we try to summarize that exact section within that health center article. Think of this like there are 200 docs today on Instacart Help Center. So we have to use RAG solution to understand the user intent, map it to embedded vectors, and find the exact section within that entire HTML to give the most convenient answer. And on the right side, we go with the API model, where we have all these buttons and we understand like APIs can help. I think that's pretty much I wanted to give thought. Like there are a little bit more detail into the architecture of this, but this might require a bit of more session. But I wanted to give a bit audience like exactly how we use LLM in what context.
Appreciate it. Any questions for Yogi? Yogi, your example of the recipes reminded me of the Instacart commercial from the Super Bowl.
Oh, yeah. I think that's the power. Like the ingestion pipeline has also helped us to launch New York Times, partnership. So New York Times cooking, like I led that integration where we brought all the New York Times cooking recipes, which are shoppable through Instacart. So that's how we start using all these kind of reusable things across.
That's great.
Yeah.
Ravi, are you all set? Does anybody else have questions for Yogi?
Okay, I'm ready.
Okay.
Let me share my screen.
Sure. Okay, let's see here. There you go. You can click hide if you'd like. Down in the next to the stop sharing. Then we'll just see your PowerPoint. Perfect.
Okay, cool.
Looks great.
Hey, hi everyone. This is Reddy Mandala, and I'm excited to to be here at the Azure and AI Show to talk about enterprise-ready Gen AI on Azure from proof of concept to secure production. Today's session is not about another chatbot demo. It's about the engineering layer that makes Gen AI secure, measurable, scalable, and reliable in real enterprise environments. So almost every organization today has experimented with Gen AI in some form. Like maybe it's a chatbot, internal assistant, a support co-pilot, or a document summarization workflow. So, but honestly, building a demo is no longer the difficult part. The real challenge begins with when organizations ask like system or like, can we audit the decisions? Can we control cost and latency? Or even like, can we operate this safely at an enterprise scale? So that's where the production engineering becomes critical. So I want to frame this talk as a practical production playbook. Like, a Gen AI demo that proves the possibility, or a production Gen AI system where that works for our accountability. So let me move to the. So the uncomfortable truth is this: so the demo usually works, but production systems fail somewhere else. So most Gen AI projects do not fail because the model cannot generate the text. They fail because enterprise systems require governance, security, identity, monitoring, and operational discipline. So leadership teams immediately begin asking different questions like, can we defend this answer? Can we trace where it come from? What happens when the model is wrong and all? So those are the production questions. What usually breaks first is the trust, or latency, or telemetry, or governance. So that's why prompt engineering alone is not enough. Then enterprise Gen AI requires retrieval, identity, orchestration, or guardrails, evaluation, and any fallback behavior. So the focus of today's session is how to move from a convincing demo to a secure Azure production pattern. So this slide shows the roadmap for the session. So first we'll frame the risk and understand why Gen AI production systems behave differently from traditional software systems. Second, we'll build the architecture using Azure native patterns such as Azure OpenAI or Azure AI search orchestration layers, enterprise data and identity. And the third, we'll discuss about the controls that includes security, guardrails, evaluation, and release gates. Fourth, we'll discuss operations because production systems require observability, latency, monitoring, incident response, and cost management. Finally, we'll discuss scaling responsibility, including maturity models and anti-patterns, organizations that can be avoided. Think of this as a production readiness checklist rather than a production pitch. So many Gen AI proof of concepts fail after the executive demo because the model is only one part of the system. The missing layer is usually the system design. The first issue is prompt only architecture, and everything depends on the prompt wording. So there's no retrieval layer, no policy engine, or no evaluation loop. The second issue is lack of authoritative grounding. So the model sounds confident, but we cannot prove where the answer came from, or it has a lack of operational ownership, where like when the cost spikes, who owns it, or when hallucinations appear, who investigates, or when prompts regress, who responds. So another major issue is lack of telemetry. Without traces for prompts, retrieval, token usage, or even latency, teams cannot debug failures. And finally, many systems have no fallback behavior. They are designed only to answer, but the production system sometimes need to refuse or even ask clarifying questions or escalate to a human. Most Gen AI failures happens outside the model. So before any Gen AI system becomes enterprise ready, 5 layers must be designed explicitly. So the first layer is identity and access, where who is asking the question, like, and what are they allowed to see. The second layer is grounding, like which enterprise source of truth should be the model rely on. The third layer is guardrails. What should the system refuse, redact, or escalate? And the fourth layer is evaluation. How do we know the system is reliable enough for to release it to production? And the fifth layer is operations. How do we monitor, debug, improve the system over the time? So production AI is not a single API call. It's an operational stack. So this diagram shows that a production Gen AI system is controlled by workflow. The user interacts through teams, portals, or enterprise applications. The request first phases through the API layer, where authentication, throttling, and validation that happens. Then comes to the orchestrator. This is one of the most important product layer. The orchestrator decides like whether the retrieval is needed or whether the tools should be called, whether the policy is applied, or whether escalations is required. So Azure AI Search provides retrieval from enterprise sources such as SharePoint, blob storage, SQL, and APIs. So Azure OpenAI that generates the response using the prompts or even system instructions and retrieved enterprise context. So across the entire architecture, horizontal layers provide identity, telemetry, private networking, and even the incident response. Azure AI it's not an architecture, it's one component inside the architecture. So the retrieval augmented generation, it's where the enterprise trust begins. Instead of allowing the model to run the model in approved enterprise content. So the process has like 4 major stages. Like first, to prepare the data through chunking, clearing, and enrichment. Second, index the data using vendor search, vector search, keyword search, or metadata. Third, to retrieve the most relevant and permitted context. The fourth is to generate the answers with citations. So these critical because enterprise systems require evidence. So the rule is simple. If the model cannot show where the answer came from, it is not enterprise ready. Security. So security must be designed before the first pilot. Enterprise Gen AI systems inherit every existing enterprise security risk and introduce new ones. It use enter ID and managed identities instead of shared secrets. Unauthorized documents that should never enter the prompt context. Keep network boundaries explicit. Redact sensitive information in logs and traces. Separate development, testing, and production environments. Or even identity is the first guardrail because it controls everything in the downstream. Let's check for the guardrails. So guardrails define the product behavior. Input screening detects the unsafe prompts and prompt injection attempts. So the retrieval control that manages approved sources and metadata filters. The tool governance controls permissions and approval workflows. Output validation checks for toxicity or unsupported claims and policy violation. Point is this: enterprise systems should not always answer. Sometimes the correct behavior is refusal, clarification, or escalation. That flexibility is what makes the enterprise trustworthy. Evaluation. Evaluation is the release gate for production Gen AI. So if few successful demos are not enough, the teams need offline testing, golden questions like adversarial prompts, human review, canary releases, continuous evaluation. We also need to measure more than the accuracy. So we should evaluate the faithfulness or relevance, latency, cost, safety, and user acceptance. Production systems should ship only when they meet quality and business risk thresholds. Observability. So So the trust requires traceability. If we cannot reconstruct the answer path, we cannot debug the system. So production GenAI systems need visibility into the prompts, retrieval documents, retrieval scores, latency, token usage, guardrail actions, and user feedback. So good observability should answer like why did this happen? Why did this answer happen? Like which document influenced it? Which like did a guardrail fire? Did cost spike? Or because no trace means no trust. Cost and latency. So cost and latency are the architectural problems in production. Unpredictable latency and cost quickly reduce the stakeholders' trust. Optimization includes routing by task complexity, catching the stable answers, limiting retrieval context, streaming the response, and even monitoring token usage per workflow. So the key idea is this: cost is driven by architecture decisions such as context size, routing, retries, and workflow design. A production system must be useful, predictable, and sustainable. Mature path. So a demo proves user experience, a proof of concept that proves the feasibility, a pilot that proves value, production proves reliability, and scaling proves repeatability. Each stage answers a different question. So the production readiness requires security review, evaluation, monitoring, rollback planning, and even operational runbooks. So the biggest mistake organizations make is skipping directly from demo to production. Anti-patterns. The common anti-patterns include direct LLM calls, giant prompts, no citations or no evaluation suits, and no cost ownership. The replacement is orchestrated workflows, retrieval with citations, regression testing, canary releases, and budget ownership. The goal is not make AI sound smarter. The goal is to make the enterprise AI safer, measurable, reliable, and useful. So the three takeaways for enterprise-ready Gen AI systems. The architecture beats the prompts. Second, grounding that creates the trust. And third, operations that decide the scale. So Gen AI becomes enterprise-ready when it behaves safely under real production pressure. Thank you all for your time and attention. And feel free to answer to any questions.
Excellent job, Ravi. I'm just going to take a look. I put a couple comments out on my Facebook and Frank's YouTube, and a link out to, or a shout out to Hoosier Chef, who said hello earlier from YouTube. Hal, Shri, Yogi, any questions?
Nope, not here. Good show.
Yeah.
Really enjoyed that presentation. It was great. Anything quick anybody would like to share that you've discovered recently or found, either AI related, Azure related, Microsoft related, platform related? I'll share this real quick. So I'm on a Mac computer right now, and I have two Logi mice with me. I've got this wireless mouse, just kind of traditional Logitech mouse, and then I also have a Logi Lift, which is a vertical mouse
as opposed to a traditional mouse where you set your hand kind of flat on it. This is more of a handshake-like position. And on either of these mice, because they're both Logi, I can actually use on Windows or Mac the buttons to control a feature Logitech calls Spotlight. So they have a physical device called Spotlight for mouse, but or Spotlight, the Logitech device, but they also now have this feature called Spotlight. Let's see if I can get it to function here. I was just playing around with it earlier. So it allows me, if I'm trying to explain how StreamYard works from a banner's perspective, or sharing your screen, or inviting other people to a meeting, it's very easy with Spotlight to actually call attention to where I am on a screen, allowing guests to stream to their own destinations. This is what allows our guests to add their own LinkedIn or YouTube channels, etc. And then when we send this link, this is the link to join the show live. So the Spotlight is a feature that comes with Logitech Spotlight devices like this. This is the Logitech Spotlight that I have from a previous event that I presented at. So it's just a Bluetooth device. It had a spot for a USB port, and then you can pair that to your computer. And if you pair that, then the Spotlight itself becomes an option to present with. Let's see if I can do that real quick here. Put it in pairing mode so it flashes on the top. Go to Bluetooth settings, scroll down, Spotlight connect. And then this new software is called Logitech Options Plus. And what the Options Plus software allows me to do is take those devices and then redefine the buttons on them and the functionality, if you will. So the Spotlight itself has the Spotlight, and then it also acts as a remote and a mouse. So I can actually go over to a different application like a browser and I can click around, or I can open all of the apps on my Mac and then go up here and maybe scroll through to PowerPoint and then open PowerPoint. And so I'm just clicking the Spotlight and then either double clicking it or clicking it once to get it to function. I think this is a double click on here to get it to open, so it's not paying attention. And then I've got keyboard shortcuts and a Logitech Spotlight for mouse presentation that I put together yesterday. So I could open that presentation. And then starting with the presentation and the Spotlight, or just, and it looks like I've got Spanish captions here, or these don't necessarily look Spanish. Maybe it's another language I selected. Some of the words look Spanish for certain, but I could figure out what language it's showing under this subtitle settings. Yeah, it is Spanish. So that's Spotlight for mouse, as well as Logitech Spotlight use.
Spiffy.
Yeah, I've been pretty happy with these devices. They're handy. But the fact that you can now use it with a Logitech mouse and you don't have to buy a specific device for presentations, if you're not giving a lot of presentations, it might be better to use it with a mouse.
That's cool.
Yeah. So I wanted to share that before we end our show here. Anything else for the benefit of the group? I think we're all US based today. That's that's not every week, right? It's usually somebody in Europe like Frank who's up late, and many of us that are up either early or middle of the day.
Yeah.
So thanks everybody for joining from around the country.
Absolutely.
Yeah.
Sure thing.
Excellent.
Thank you for hosting this.
Yeah. It looks like we've had somebody was asking like the reach or the how many people join us live. It's typically anywhere from 3 to 5 if we don't do any kind of advertisement. But if you're speaking on the show, you're more than welcome to share the link that Frank sends out and send that to your own LinkedIn network. If you have a YouTube channel or Facebook or any other kind of social media, StreamYard makes it super easy. You just set up a free account, no passwords to maintain it. We'll send you an email code to set up your account, and then you can attach it to 2 of your social media platforms. So you can go live on your own LinkedIn, you can do Facebook, you can do X if you have a premium subscription, if you have enough TikTok followers, you can go live on TikTok. There's I think 30 choices of different social media that you can set up. So really the reach of the show is up to each and every one of us. The more we share the link, and then this goes into like a, watch the previous show type setup in YouTube and Facebook and other platforms. So if you don't join us live, you're more than welcome to ask questions, and hopefully at least myself and Frank typically monitor those different channels, but that's an easy way to get in touch with us. And many of us, I think all of us, have our social media or at least our names on social media listed here, so you can find Hal and Ravi and Shri and Yogi, as well as myself, Dan, on LinkedIn and elsewhere on social media. So feel free to connect. Thanks everybody for joining.
Excellent.
Thank you.
I'm going to go ahead and click the end stream, which will shut off the